Hello, today we are looking at a new video in which I present you advanced pumping systems. So we are going to look at a little bit of fluids, mechanics of fluids, but with a more engineering approach. So we have a pump here, and we have various um, objects that are linked with it. So it can need water, it can furnish water, it can store water, like here. Usually you want to have a certain flow rate, which is the velocity multiplied by the surface of the pipe, um, which represents the flow of matter that is transported. And you also want to have a certain pressure. So we will see how that works exactly. And finally, we have a certain height that will require some energy, because here it starts in the bottom and here it ends on the top. So at first we need to look at the generalized Bernoulli equation. So there are two versions of it. This is the world in pressure, in terms of pressure. So everything is homogeneous to a pressure that is a density of energy in terms of volume. So this is the the volumic density of energy, kinetic, potential of gravity, and pressure. With the normal Bernoulli equation, it will be equal to 0, but it's not equal to 0, and we call that term head, and in this term the head in pressure, and here the head in height, and I called it HMT, and we'll see that later why I called it HMT. So we move from the first equation to the second by dividing by uh, rho g, with rho the density of the fluid, and g the constant of gravitation. Um, so HMT stands for hauteur manometric total, so total manometric height. It's a characteristic of the pump and what will be the most important part. So we'll see that in the end. It's homogeneous to height, so in the equation in height. Um, but first we need to calculate the the head loss in terms of pressure, or in terms of height, relative to what we want to furnish to the fluid. So uh, it's also called the charge in French. So when it's not a pump, we'll note our HMT to be delta H, because it's more convenient. And when we talk about a pump, we call it HMT. So it represents the height that should be added to fight against the head loss. Yeah, the head, I wrote a lead. So at first we need to define how the fluid flows, and we calculate a number, characteristic number called the number of Reynolds. We need to calculate dH times the velocity of the fluid divided by a certain viscosity. So there are two kinds of viscosity. I'm not going to enter too much in detail. You probably know about that already. If it's below 2000, it's a laminar flow. If it's above certain number, above 2000 and some hundreds, it's a turbulent flow, and else it's in an unknown transition state. So we will try to define two kinds of head losses. The first is called regular. So it means that on each meter of the pipe, you will lose a certain amount of energy, and this loss will be regular. So every time you walk, you lose you lose a certain energy on each step. Um, So we use the equation of Darcy-Weisbach. So in a pipe, the head loss, the regular head loss, is equal to lambda L over dH times V squared over 2G, with V the velocity of the fluid, so it circulates from front to back. L stands for the length of the pipe, so the transversal length. DH is the ratio of 4 times the surface, so this surface here in green, and PM stands for périmètre mouillé, so it's the perimeter, so it's this length plus this length plus this length plus this length. With lambda, the coefficient of regular head loss. So we use experiment results to show that lambda is equal to 64 over RE. And in a cylindrical pipe, we get a special equation that is called the equation of Hagen-Poiseuille. And we introduce QV, the flow rate, that is just the integral of VDS, which is just VS in most systems. So now that we have our equation in a laminar system, we can try to get it for a turbulent system. So we call a coefficient called rugosity. It measures the property of the material to be non-homogeneous. So small hips in the material, how it's not homogeneous, so spikes. If epsilon is very small, there is no influence of the rugosity, so we get the result from laminar flow. If Re is kind of small, we can use the formula of Blasius. And else we need to use the formula of Karman-Pront, that is not a explicit formula because you have twice the unknown, that is lambda, which is kind of annoying, but you need a computer to solve it. And even more, you can use the general equation called the equation of Colebrook. That is this one, which is very huge. Obviously, you need a computer to compute it. Singular head loss. So once you've calculated the regular head loss, you need to take account the shifts in geometry. So when the pipe system turns, when it shrinks, when it expands, so this loss is spatially instantaneous, so unlike the regular ones, and they add up with the regular head loss to be calculated, and they are given by empirical tables. You can find it on the web pretty easily, and they are usually very small unless you are doing some weird path. And this depends on the path, obviously, chosen by the fluid. So when you buy the pump, you have calculated the loss, that is the sum of the regular loss plus the singular loss. So this is the work that you usually do in baby classes. But when you buy the pump, you want to have a certain you want to have a certain energy that is furnished to the fluid that gives enough to at the same time furnish the power to go from point 1 to point 2, but also fight against the losses. So it's pretty straightforward. You have the shift in potential energy, the shift in kinetic energy, the shift in pressure in that term, plus the loss, so singular and regular ones. But you also want to have a certain rate because you don't want to have a good pressure but a very slow fluid, because if you have a low flow rate, the HMT will convert mostly into pressure, but your fluid will be very slow. So what you want to do is you want to have to characterize your system by a couple of HMT, energy required, and QV. So pipe markets send usually you have this sort of diagram in which you have HMT, so it's homogeneous to height, and so it represents energy, but the part that goes into pressure more than anything, and QV represents the flow. And this represents where the pump can actually deal with the fluid, which means that if you stay at a certain QV, you'll end up with a certain HMT, and with a certain HMT, you'll end up with a certain QV. HMT as a function of QV is always decreasing. However, sometimes you can't have both HMT and QV, and this is the reason for the last part of the diagram. We had a third axis with eta, so eta is the Greek letter for efficiency. So it's on a third axis, usually a different color. It's a percentage of the power that is actually furnished. Usually it's represented on the QV axis because here you can directly read the percentage of energy that is furnished to the fluid. And you can see that this pump works pretty fine between those two red lines, meaning that even if it doesn't exactly fit the correct HMT QV couple, you can find some intermediate results, and you can still buy the pump even though it does not perfectly match your system. And this is pretty useful because even though you might have an HMT QV on this diagram that is very close to what you want, but a poor efficiency at the difference, meaning that it will work very fine near the line, but not very well somewhere else. So that's all for this video. I hope you enjoyed it. If you have any questions, feel free to ask them in the comment. I'll be glad to answer them. And bye.